Now that we've introduced the idea of the natural exponential function and done a few examples, it's helpful to go and start talking about calculus, since that's sort of the domain of what we're talking about anyway. And the way we can talk about the calculus of that e function is to recall some of the things we've already learned. For instance, we know that the natural log and e to the x are inverse functions. So natural log of e to the x equals x. We also know that the derivative of the natural log is 1 over x, and that in general the derivative of the natural log of something is 1 over something times the derivative of that something. And another way to write that is simply it's 1 over the function times the function's derivative. So knowing this, what we can do is we can set up this statement here, and we can take the derivative of both sides. So in doing that, we know that the natural log of e to the x is equal to x. If we take the derivative of both sides, we know that the derivative of x is simply 1, so that's simple enough. But this derivative is 1 over e to the x times the derivative of e to the x. That's the definition. But this is what we're trying to find, the derivative of e to the x. So I simply multiply e to the x over here. But I get that the derivative of e to the x is e to the x, which is kind of an interesting result. So one thing that's really, really neat about the exponential function is that it's the only function that is well, except for the zero function, but it's the only non-zero, non-constant function that is equal to its own derivative everywhere. So if you're taking the derivative of e to the x, it's just e to the x. You don't have to think about it, don't overthink it, it just is equal to e to the x. That's a really cool result. And what makes it extra neat is because it's its own derivative, it's an antiderivative for itself as well, right? Because that's how the relationship works. Now, be careful that when you take its antiderivative, it's equal to itself plus a constant, right? That's the definition of antiderivatives, is that the general antiderivative has an arbitrary constant. So be careful in that regard. But it also has some neat, very straightforward properties. So by the chain rule, since the derivative of e to the x is e to the x, the derivative of e to something is e to something times the derivative of something. That's just the straight chain rule, right? That's sort of the inner function, outer function situation. Anyway, as a result, let's say that this wasn't x. Let's say it was 2x. So you'd have e to the 2x times the derivative of 2x, which is 2. So 2e to the 2x. For 4x, it's e to the 4x times 4, or 4e to the 4x. Or let's just say it's some arbitrary number, a. It'd be e to the ax times the derivative of ax, which is ae to the ax. So hopefully you're noticing a pattern. It's that e to a number times x, the derivative is simply that number times e to the number times x. So if it was e to the negative 14x, it would be negative 14e to the negative 14x would be the derivative. I didn't write that, I should have. This should be like d dx. Right, I'm sorry, I apologize for that. But the idea here is that derivatives are fairly straightforward for e functions. In general, it's whatever you started with times the derivative of whatever that exponent is.